Sharing with graph states. This is the improvement. Okay, so first I want to thank the organizers for this nice workshop. Today I want to talk about quantum secret sharing with graph states. This is a joint work with Sylvain Gravier, Jérôme Javel, and Mehdi Mallah. And what I'm going to talk about is mainly based on these two papers. Okay, so what is the context? The starting point of this line of research is this paper by Damian Markham and Barry Sanders, which is graph states for quantum secret sharing. And the idea is to consider a particular family of quantum secret sharing schemes which are based on graph states. And the motivation is that the graph states are very promising in terms of physical implementations. So by considering this particular family of quantum secret sharing, somehow we guarantee that if we end up with a scheme, with a quantum secret sharing scheme, then it's probable that we can implement this scheme. Okay? So it's somehow we are working with some constraints coming from the physical realization. Okay? If we are working with graph states, we know that it's promising for the physical implementation. But on the other hand, the question is how good are these protocols for the secret sharing part? Okay, we are working with these constraints, and the question is how good the protocols are. Okay, and this is the question I want to address. I want to show that actually we can use these kind of protocols to do secret sharing. Okay? It's not only interesting for the physical implementation; it's also interesting for secret sharing. Okay. The techniques we are going to use are coming from quantum information processing techniques, including quantum cryptography, but thanks to the graph state formalism, we are working with graphs, and we are going to use lots of graph theory, as you will see. Don't be afraid about that. I will try to explain it carefully. And we will also use probabilistic methods, like the Lovász local lemma, which is a very powerful tool, as we will see. Okay, so the applications, so of course it's for quantum secret sharing, but we can also combine this scheme, quantum secret sharing, with other protocols like quantum key distribution, and we obtain a kind of quantum key distribution with several players. It's interesting. And there are also some side effects for the other application of graph states, because graph states are used, for instance, for quantum codes, quantum correcting codes with the graph codes. It's used in blind quantum computing. It's used in measurement-based quantum computation in general. And if we have a better understanding of the properties of the graph states in this context of quantum secret sharing, it's also good for the other applications of graph states. Okay, so let's start with the secret sharing. So secret sharing is a protocol which has been introduced at the end of the 70s by Shamir. And so the idea is that you have a secret, your testament, your will, and you want to share this secret with your friends, that you don't really rely on your friends. So you want to have a threshold k, such that if more than k players work together, collaborate, then they are able to recover the secret. But if there are less than k players, you want to avoid them to have any information about the secret. Okay? You want to guarantee that they have no information about the secret if there are less than k. This is a threshold scheme. And it's actually possible to implement these kind of schemes in the classical case, so as it has been proved by Shamir. For any number of players and any threshold k, there is a way to do a kn secret sharing scheme. And the idea is that you are using polynomials, and the basic idea is that if you know k points of polynomial of degree k minus 1, just by doing some interpolation, you can recover what is the polynomial, and you recover the secret. So it's simple and nice, but I will not go to details, because what we are interested in is the quantum case. Okay, so now we have a quantum secret, a qubit, the state of a qubit, and we want to share this quantum state. So we encode this state into a larger state, possibly a density matrix, a mixed state. And again, we want to have a threshold such that if we have more than k players, they can recover the secret. It means that they can reconstruct the state ket phi. If they are less than k players, they have no information about the secret. So first remark is that because of the no cloning, the threshold must be larger than n over 2. Indeed, suppose that the threshold is less than n over 2, then it means that two distinct set of players, for instance these two and these two, can recover the secret. Okay? And if they can recover the secret, it means that they can reconstruct the state. So these two guys are reconstructing a state phi here, these two a state phi here. So it means that starting from one copy of the secret, you have two copies of the secret. This is the cloning. Okay? So to avoid this cloning, the threshold must be larger than n over 2. So it's a necessary condition, and it turns out that this is somehow a sufficient condition because Gottesman showed that for any number of players and any threshold larger than n over 2, there exists a quantum secret sharing scheme.
So,
Yes?
is it possible to have a secret sharing that has the property that although the threshold is less than n over 2, but if a bunch of players recover the secret, is locking the information so that despite the fact that it was less than n over 2, but is not violating no cloning anymore. So I get few people.
It will not be a threshold protocol.
Why? I'm saying that like as whoever got it first, the three people who got it first and managed to recover it, then they are locking the information.
Yeah. But if they are able to recover the secret without communicating with these guys, and these guys are able to recover the secret without communicating with these guys, then it means that they can do it independently, so they can do the cloning. Okay, so we can do a secret sharing scheme for any threshold larger than n over 2. But this is not the end of the story, because this protocol introduced by Gottesman has several limitations, and the main limitation is that the size of each share, that is the size of the system that you give to each player, is increasing with the number of players, and is increasing linearly with the number of players. So it's a big limitation for the physical implementation of the protocol. Okay, it's the values. Okay, so the approach of Markham and Sanders is to consider secret sharing schemes with graph states, where we have the following constraints. The first one is that to avoid the fact that the size of the share is increasing, we want to force each player to have a single qubit. Okay. Each player is having a single qubit, and the state which is shared by the players is a graph state. And the good news is that the graph states are promising for physical implementation, so it's a good assumption somehow. And the protocols is as follows. So we have a graph which is describing the protocol. So here it's a C5, a pentagon. And this graph is describing the state shared by the players. So each vertex represents a qubit. And the secret is encoded as follows. So starting from a secret S, the state which is shared by the players is this one. So I will not go to the details, but here we can see that it depends on the secret, of course, and it also depends on the graph. AG is the adjacency matrix of the graph. And if the secret is 0, here you have the graph state represented by the graph. Okay? And if the secret is 1, you have the graph state where you apply Z, Pauli Z, on all the vertices, all the qubits. Okay? So this is how the secret is encoded into this state, which is shared by the players. Okay, so this is the protocol. Now the question is, what kind of threshold we can do with this kind of protocol, and what are the interesting graphs? To answer this question, we need some graphical characterization of the accessibility properties of the protocol. And the key notion here is the odd neighborhood. So when we have a graph, D is a subset of vertices, and the odd neighborhood of D, odd of D, is composed of the vertices which are outside of D and which have a non-number of neighbors in D. Okay, so the blue vertices here. Okay, so the blue vertices have 1 or 3 neighbors in D, so it's odd. And these black vertices are not in the odd neighborhood of D because here we have 2 edges and here there are 0 edges. Okay, so the odd neighborhood, so we have this parity condition, okay, for defining the odd neighborhood of a set of vertices. And we say that the set B is oddly dominated by the set D if B is in the odd neighborhood of D. Okay? If B is composed of blue vertices only. And this notion of odd neighborhood is important for quantum secret sharing because we have proved that with Elham Kashefi, Damian Markham and Mehdi Mana, we have proved that when the secret is classical, okay, here we consider the case where the secret is classical, it's just 0 or 1, then a set of players can recover the secret if and only if this set is not oddly dominated. If you are oddly dominated, it means that you cannot recover the secret, the classical secret. Okay, so we have a characterization of the set of players that can recover the classical secret using this odd neighborhood. Okay, so according to this property, a natural quantity to look at for a graph is kappa of G, which is the max of all the odd neighborhood. Okay, it's the greatest odd neighborhood in the graph. And as a consequence, we have the following properties, which is that if you take a set of players which is larger than kappa of G, then you are guaranteed that this set of players can recover the secret. Okay? This set of players cannot be oddly dominated because it's larger than the largest odd neighborhood, so this set of players can recover classical secret. Okay, so let's have a look to an example. So for the C5, so kappa of this graph is defined as the max of the odd neighborhoods. So let's start with a single vertex. So if I look at the odd neighborhood of a single vertex, this odd neighborhood is of size 2. So it means that kappa of this graph is larger than 2. Okay. Now if I take 2 vertices in the set D, so for instance, let's take 2 vertices which are connected by an edge, then again the odd neighborhood is of size 2. If I take 2 vertices which are not connected by an edge, the odd neighborhood is again 2, because this guy is connected to red vertices, but with 2 red vertices, so it's not in the odd neighborhood. Okay, and that's it. Because if I take a larger set D, the set which is larger than 3, since the odd neighborhood is outside of D, the odd neighborhood will be smaller than 2. So it means that the kappa of this graph is just 2. Okay, the largest odd neighborhood in this graph is of size 2. Any questions so far? Okay. Okay, so now what about the quantum case? So we have seen that if set of players is larger than kappa of G, then the players can recover a classical secret, but what about the quantum secret? We have this nice characterization which says that, which is due to Damian Markham and Barry Sanders, which says that a set of players can recover a quantum secret in a protocol described by G if this set of players can recover a classical secret in G and in G bar. Okay, in the 2 protocols G and G bar, where G bar is the complementary graph. Okay. So thanks to this theorem, we consider this quantity, kappa Q of a graph, which is the max of kappa of the graph and kappa of G bar, of the complementary graph. So if you are able to recover a classical secret in the graph G and in the graph G bar, you are able to recover the quantum secret. And so similarly, now if we take a set of players which is larger than kappa q of G, then the players in B can recover the quantum secret. So this is the quantity which is important. Okay, when we have a graph, we want to know what kind of quantum secret sharing scheme we can do with this graph. We compute kappa q of the graph and we obtain the bound on the threshold. In fact, it's not actually a threshold, because here we guarantee that if we take a set of players which is larger than kappa q of G, then they can recover the secret. But in order to have a secret sharing scheme, we want to guarantee that if we take less than this number of players, they have no information about the secret. And in fact, this is not the case. And this is not the case at the moment, because they may have some partial information about the secret. Okay, here it does not say anything about the sets which are larger, which are smaller than kappa q of G. So in order to make, in order to have a threshold scheme, we take this protocol based on graph states and we add two ingredients. The first ingredient is to have a preliminary encoding of the quantum secret with a classical key, a random classical key, which is chosen between 0 and 3. And in fact, this encoding is nothing but a quantum one-time pad. Okay, so that is, we apply a Pauli C, the corresponding Pauli operator on the secret. And it guarantees that if you don't have the key, you have no information about the quantum secret. Okay, so it's the usual quantum one-time pad. And now we take this classical key and we share this classical key to the players using a classical secret sharing scheme. And we choose the threshold of this classical secret sharing scheme to be K. As a consequence, if we take a set of players which is larger than K, they can recover the quantum secrets thanks to the previous property, and they can recover the classical key because of the classical scheme. So they can recover the quantum secret. And now if we take a set of players which is smaller than K, because of the classical part here, they don't know the classical key, so they cannot recover the quantum secret. And we guarantee that they have no information about the quantum secret. Okay? So by adding this quantum one-time pad and the classical secret sharing of the key, we guarantee that we have a threshold scheme. Okay? Okay, so let's have a look to several examples. So first, my favorite graph, the C5, the pentagon. So we have seen before that the kappa of this graph is 2. And if we look at the complementary graph, which is this one, so we replace edges by non-edges and non-edges by edges, okay, it's the complementary graph. It turns out that this graph is the same as the previous one, they are isomorphic. So the kappa of this graph is also 2, so the kappa q of the graph, which is the maximum of this one, the kappa of this one and the kappa of this one, is also 2. So it means that using this C5, we can realize a 3-5 protocol, which is optimal because we know that a 2-5 protocol is not possible because of the no cloning. Okay. So that's the good news. Now, if we consider a complete graph for any number of vertices, if we consider a complete graph, all the possible edges between them. The kappa of this graph is n-1, because if you take just one vertex, all the other vertices are in the odd neighborhood of this guy. Okay. So the kappa of this graph is n-1. So the complement is the empty graph. The kappa of the empty graph is 0. So the kappa q, which is the max of n-1 and 0, is n-1. So we can use this complete graph to realize an NN protocol. That is a unanimity protocol. We need all the players in order to recover the secret. So this case is interesting for two reasons. The first one is that, in fact, the complete graph is nothing but the GHZ state. And so it's this usual state. And moreover, it turns out that broadband, Schwa, and TAP have introduced a quantum secret sharing scheme which is based on GHZ state. And it turns out that, in fact, it coincides with this protocol. Okay? For this particular kind of state, if we consider the GHZ state, we obtain exactly the same protocol as broadband, Schwa, and TAP. Okay. Now let's have a look to another kind of graphs, which are called the Paley graphs. So what is a Paley graph? So take a prime number, n, which is equal to 1 modulo 4. So there are plenty of such prime numbers, for instance 5, 13, 29, there are plenty of them. Okay? So you consider the corresponding graph state. And so the vertices of the graph are the integers between 0 and n minus 1. And you put an edge between two vertices I and j if I minus j is a square. So if I minus j is a square, then you put an edge between the two vertices. And it turns out that we have proved that the kappa q of this graph is smaller than n minus square root of n. It's just an upper bound. Okay? We don't know exactly what is the kappa q of this graph, but it's smaller than n minus square root of n. So as a consequence, using Paley graphs, we can implement such a protocol where the threshold is n minus square root of n. So here, the point is that we are looking for a graph with a small kappa q. Okay? And here, at the moment, we are able to do n minus square root of n. So it's not very small, but in order to have a smaller threshold, smaller kappa q, we considered the following construction, which is based on the lexicographic product of graphs. So here is the definition. So if you take two graphs, the product of these two graphs is this one. So the idea is that you take the first graph and you replace every vertex of this first graph by a copy of the second graph. Okay? So you put triangles here, here, and there. And if there is an edge here in the first graph, you put all the possible edges between the two copies. Okay? This is the lexicographic product. And we can show that the kappa q of a graph, when we do the lexicographic product, evolves as follows. Okay, so we have this equation where the star is the lexicographic product of the G and G. And using this formula, we can prove that if we start with the C5, the pentagon, and we do copies of these ones, and we do the product of C5, then we end up with a protocol where the threshold is n minus n to the 0.68. Okay. So it's better than the previous one. Okay. Before we had n minus square root of n, so n minus n to the 0.5. Here it's better. And you can do something even better if you start off with the Paley graph 29. So you can compute the threshold in that case, and you obtain this n minus n to the 0.7. And this is the best construction we know, in fact, for secret sharing with graph states. Okay, the best construction we know is this one, is the lexicographic product of Paley graphs, which gives us this threshold n minus n to the 0.71. It's not so good because asymptotically this threshold is n, okay? Because it's n minus something which is small comparing to n. So the question is it possible to have a family of graphs such that the kappa q is not n minus something, but Cn, okay, where C is a constant. This is a linear threshold. Okay. Okay, so we are not able to construct such a family. However, it exists. It exists some graphs which have a linear threshold. In fact, we have proved that for any n big enough, there exists a graph of size n such that the kappa q of this graph is smaller than 0.811n. So it's possible to have this linear threshold, okay, and the constant is 0.8. So how to prove that? How to prove the existence of such graphs, of such secret sharing protocols? We are using a probabilistic method, and in particular the powerful Lovász-Local lemma. So here it's the lemma which is presented in the no independency case. It's a particular case of the Lovász-Local lemma. So it's a probabilistic method. So we are considering a series of events, A1 to AK, and we consider that they are bad events. So it means that, in fact, we are interested in the case where none of these bad events occur. Okay, we are interested in the case that none of these bad events occur. And now suppose that we are able to give a weight to each of these events, W1 to WK, such that the probability of the event, AI, is upper bounded by Wi times P, where P is this product. And if it is the case, then the probability that none of the events occur is greater than P, which is non-negative. So in the case of the graphs, if we are looking at graphs, if the probability is larger than 0, it means that there exists at least one graph which is satisfying this property. Okay? There is at least one graph which have no bad events. So it's a powerful tool, and so here we are applying this Lovász-Local lemma to prove the existence of graphs. So here is the proof. So it's a bit technical, but I want to briefly show you how it works. If you don't like probabilities, wait for the next slide. Okay. Okay, so kappa q of the graph is smaller than Cn. By definition, if and only if the odd neighborhood in the graph, for any set, the odd neighborhood in the graph and in the complementary graph are smaller than Cn. Okay, for any set of vertices. Here we are considering just sets of vertices which are smaller than 1 minus Cn, because if we take a larger set, D, by definition of the odd neighborhood will be smaller than Cn. Okay, so we don't really need to look at that. We just need to look at the sets which are smaller than 1 minus Cn. Okay, so we want to have all these odd neighborhoods smaller than Cn. So we take a random graph. Here it means that we take a graph with n vertices, and where for every pair of vertices there is an edge with probability 1/2. So we take this random graph, and the bad events are that the odd neighborhood of D is larger than Cn, and the odd neighborhood of G bar is larger than Cn. Okay, for any set. So these are the bad events. We don't want them to occur. Okay, so now if we fix a set of players, a set of vertices, and a vertex U, the probability that this vertex U belongs to the set D, to the odd of D, is 1/2, because every edge here occurs with probability 1/2, so it's easy to see that the probability that U is in odd of D is 1/2. Okay. Moreover, if now we consider another vertex V, then the probability for V to be in the odd neighborhood of D is also 1/2, and this probability depends only on these edges, which are different from the previous edges. Okay, it depends on distinct edges, so we can conclude that these two events are independent. Okay, the fact that U is in the odd neighborhood and V is in the odd neighborhood are two independent events. So as a consequence, the size of the odd neighborhood, which is the size of the odd neighborhood, can be seen as a sum of independent variables, independent Bernoulli variables. Okay, so as a consequence, we can write down the probability as follows: the sum for j equal to 0 to this quantity. J is the number of vertices which are not in the odd neighborhood. Okay, so it's just standard techniques to write down this probability, and we can upper bound this probability by this quantity, where h is the binary entropy. Okay, so we have an upper bound on the probability for the odd of d to be larger than Cn. We can do the same in the graph G bar, the complementary graph, in the same bound. Okay, and now we choose the weight. We choose the weight Wd and W prime d to be this one. 1 over n times n choose d. Okay. We compute P, which is the product of all the 1 minus Wd, 1 minus W prime d. And it turns out that this P is larger than this quantity. Okay, don't go to the details. Okay, so we obtained that, and now we are ready to do a numerical analysis, and we show that if C is, we see that if C is larger than 0.811 and n is big enough, then it turns out that we have this inequality. And if we replace, and thanks to the previous inequalities, we obtain that the probability of AD is smaller than WDP. And this is, and so we meet the requirements of the Lovász local lemma. So as a consequence, there exists a graph such that the kappa q of this graph is smaller than 0.811 n. Okay? Okay, so okay. After this proof, which was a bit technical, sorry about that, let's go back to this property. So we have proved that for any n which is big enough, there exists a graph of order n such that the threshold of the corresponding secret sharing scheme is smaller than 0.811. So it's a bit frustrating because we are not able to construct such a protocol, such a graph, but they are existing. Okay, there exists at least one graph for any n which is satisfying this property. So one possible interpretation is to say that okay, so there are some graphs which are satisfying this property, but maybe they are very rare. Okay, it's not a common property to have a small kappa. But this is not the case. In fact, using the same techniques, again the Lovász local lemma, we can show that almost all graphs are satisfying this property. That is, if you take a random graph and you compute the kappa q of this graph will be smaller than this quantity with probability which is almost 1. Okay. It's 1 minus 1 over n. So it means that almost all graphs are satisfying this property. And we are not able to construct any of them.
Just a randomly picked one, it will be.
Yes. Yeah. So, okay, so we are not able to construct them, but it's a good news because it gives us a way to generate a good graph. Just pick a random graph. Okay, it's quite simple. Pick a random graph with high probability. This graph will satisfy this condition. Okay, the threshold of this graph will be smaller than 0.811 n. And then it would be good to double check that the kappa q of this graph is actually smaller than 0.811 n. Okay? Before using this graph, we want to double check that it's actually smaller than 0.811. Unfortunately, this is not efficient. So the sampling part is efficient. That is, we take a random graph, and if this random graph is not a good one, we can just take another one, and the number of loops here is very small. because we obtain a good graph with high probability. So this part is good. The number of sampling is small. But the non-efficient part is the double checking. Double checking that the kappa q of the graph is smaller than 0.8 n is hard. Okay, deciding this is hard. In fact, we proved that the corresponding decision problem is NP-complete. So if you're not familiar with NP-complete, it means that there is no efficient algorithm, no polynomial time algorithm, unless P equal NP, which is unlikely. Okay? So there is no efficient algorithm for deciding this. So to prove that, first we need a bound on the kappa of the graph. If we take a graph of size n, and where the degree is delta, so the degree is the maximum number of neighbors for a vertex, then the kappa of this graph is always smaller than n delta over delta plus 1. So the reason is the following, it's not hard. The fact that D and all of D are distinct sets means that the sum of the two is smaller than n. Okay. If you look at the size of D and the size of all of D, the sum of the two is smaller than n. And moreover, since the degree of the graph is delta, the odd neighborhood is smaller than delta D, because every single vertex in D has at most delta vertices outside, delta neighbors outside of D, so the odd neighborhood must be smaller than delta times the size of D. Combining these two inequalities, you obtain this and then this, which is what we want to prove. Okay, so we have this upper bound, and is it possible to reach this upper bound? The answer is yes. If we take a regular graph, all the vertices have the same degree. Then we have that the kappa of this graph is equal to this bound, if and only if there is a set D of particular kind. The set D must be an independent set, that is, there is no edge inside D. And moreover, if you take any vertex which is outside of D, this vertex has exactly one neighbor in D. Okay, to see that, in fact, you can just take these two inequalities and look at the case where they are saturated. Okay? Replace these two inequalities by equality, and you can see that you end up with this condition. There is no edge inside, and every vertex which is outside of D must be in the odd neighborhood, and so on. Okay? So we have this condition. And it's interesting because this kind of set, an independent set such that all the neighbors outside have only exactly one neighbor inside, is called a perfect code. Okay? It's known in graph theory, and it's called a perfect code. Okay. So we reach this bound if there is a perfect code in the graph. And we use this property to prove that the problem is hard, is NP-complete. Because, in fact, we know, it has been proved by Kratochvil that this problem, deciding whether a graph has a perfect code, is NP-complete. So we use a reduction to this problem. Okay, we take a delta regular graph, we ask if the kappa of the graph is bigger than this quantity, which means, as we have seen before, that there is a perfect code in the graph. And since this problem of deciding whether there is a perfect code or not in the graph is NP-complete, we obtain that this problem is also NP-complete. In fact, it means that the problem is NP-hard, and the fact that it's NP is simple. There is a polynomial certificate, which is just the description of a subset of vertices which odd neighborhood is larger than K. Okay, so we obtain the NP-completeness of this problem. And we are interested in fact, the quantum version, that is kappa q of the graph, and using another reduction, we show that it's also NP-complete. Okay, so to conclude, so we have considered these quantum secret sharing schemes which are based on graph states. We consider first constructive families of protocols of graphs, and we obtain that we can do this kind of thresholds, n minus n to the 0.71. We proved that there are graphs. There exist some graphs with a linear threshold, but we are not able to construct them, unfortunately. We have a nice procedure for generating good protocols. That is, just take a random graph. In fact, if you don't really care about the fact that the graph you obtain is actually having a linear threshold, then it's okay. Because the probability that the graph has a bigger threshold is very small. But if you want to double check that the threshold is actually linear, then you have the problem that this double check is not efficient. And finally, there is a lower bound. I haven't talked about that, but we can also prove a lower bound on the kappa q of a graph. So from the no-cloning theorem, we know that the kappa q is always larger than n/2. And in fact, we are able to prove a little bit better. We prove that it's greater than n/2 plus n/156. It's a small improvement to the no-cloning theorem. Okay. Thank you.
Existence theorems, you have this integer n0, then it was n greater than n0. Do you have a bound for the n0?
So n0 is it's 10 to the 4. Not too bad.
So in order to attack your way out for this double checking problem, so it's wonderful to have the secret sharing with low threshold. So what if you just randomly pick, as you said, and we go ahead, we do your scheme. We know that things don't go wrong because we have this classical secret sharing that you put on top.
Mm-hmm.
So if lower people try to do, they won't get away with it because we set the threshold to this low threshold for the key. Now the problem is that now the good party will get together and they recover the secret. They are not sure that they actually have the secret.
Exactly, yes.
So, but then, instead of trying to check it with the kappa, so why can't we add some sort of trap there? That, they measure those traps, so there's some extra things that from the dealer already put there that not only they are supposed to get the secret, but they have a bunch of other qubits that at the time that they recover the secret, they are measuring those flags. And if those flags were 1, they know that their secret sharing was correct. I'm just trying to write it. This should not violate the NP-completeness result that you're saying because now we're changing the protocol.
So you just want to let them know that they are not able to recover the secret.
Yeah. So this way is basically we never calculate that bond. We're not checking that bond. We just said, okay, just go ahead, pick up this randomly, and we know that nobody can cheat because of the classical part.
So if they know the graph, so for a given set of players, they know if they are able to recover the secret or not. They can double check it in polynomial time. For a fixed set of players, deciding if they are able to recover the secret, this is easy.
So why should we bother even to check that the kappa is less than that?
Because there are an exponential number of subsets. So you cannot check all the subsets.
So that's what I'm saying. I said let's not check those subsets for the graphs because of this expansion. Let's just pretend that it is possible. Right, we can discuss it. to see if we can.
So these secret sharing schemes are closely related to quantum error correcting codes. Does this random graph theory result give us the construction more efficient quantum error correcting codes?
So this is the next step. We are looking at this. Yes.
So does the classical secret sharing, does that really have this property that if you don't have enough of the party to get no information at all, it's completely flat?
Yes, it's completely flat. If you don't have enough, we have 2 minutes. I can try to explain the classical secret. 1 minute. Oh. So the idea of the classical secrets, you choose a random polynomial of degree k minus 1. Okay. The degree of the polynomial you choose is k minus 1. So you choose this random polynomial such that the constant term is the secret you want to share. Okay? So you have a polynomial like this, and so here is 0. So here it's the secret. And now to each player you give 1 point, which is this one for player number 1, this one for player number 2, and so on. And now if you take k players, at least k players, then they know k points of the polynomial, so they are able to recover, to interpol the polynomials. So just by an interpolation they know the value of the secret. And if you know less than k players, there are plenty of polynomials. For any possible secret there is a polynomial which is going through these points, so they have no information about this. So what is important is to take here to work with a finite field instead of the real, so it guarantees that they have no information about the secret.
Alright, how much time? Let's thank someone again.